Welcome back, everyone. This is Chapter 2, Nonlinear Functions and Models. And the claim is there's a lot more nonlinear functions out there than there are linear. So we're going to take a step up in the difficulty here and do Section 1, right, quadratic functions and models. Right, so these are slightly more difficult than linear functions and models. And the claim is there are a lot of physical and economical models that are created using quadratics. So this is kind of a very natural step to go to. So let's get a definition here. Let's remind ourselves, right? A quadratic function is a function that can be written in the form either f of x is equal to ax squared plus bx plus c, or if you'd like, you can just use y, right? Y is equal to ax squared plus bx plus c. And there's some conditions, right? So of course, a, b, and c should be fixed numbers. Should think of these as constants, right? So fixed numbers or constants. And we should have a is not equal to 0. And we'll get into why we want that here in just a second. The shape of a graph of a quadratic function is called a parabola. Parabola. There we go, and this looks like a U sort of shape. You've probably seen one before. So before we get into some examples, there's some properties of quadratics that are pretty important. We need to go over these really quick. So this is a nice big old theorem here. We can prove all of these things. That's why it's a theorem, not just a definition or anything. And this relies on our quadratic. So ax squared plus bx plus c, so long as a is not equal to 0. So the first thing is there's something called a vertex. So a vertex. A vertex is the point where the parabola turns around. And actually, we know a formula for it here. The x value is always negative b divided by 2a. So remember, we get these b's and these a values up from our function here. And then the y value, well, the easiest thing to do is just say, well, take the x value and plug it into the function. So f of negative b over 2a. So plug in the x value into your function, and that'll give you the correct y value. So let's go ahead. I'm going to draw a quick graph here. I've left myself some room. So here's maybe an x-axis and a y-axis here. And I'm going to graph maybe a parabola. So here is a parabola. It looks like a U shape, like I mentioned. And right here, this is where the vertex is. So this is what the vertex looks like. It's, again, the point where the parabola turns around. Okay. So, next, the y-intercept. Intercept occurs when x equals 0. So when x equals 0, this is the y-intercept. Sometimes I denote this just as y-int. Right, for intercept. Likewise, the x-intercept. But in this case, sometimes there's multiples, right? So x-intercepts occur when y equals 0. So when y equals 0, that's going to actually be right here and also right here. So this is an x-intercept. And this point right here actually is an x-intercept and a y-intercept. How nifty. So in order to solve for x-intercepts, the claim is we can either use the quadratic formula, which you may remember, or we can sometimes use factoring. And this is how we solve for our x-intercepts. The next thing, turns out parabolas are symmetric. Symmetric. About the line, it's a vertical line, so vertical lines are x equals something, and it's the vertical line that goes through the vertex, negative b over 2a. So let me go ahead and draw maybe in red here. Vertical line that goes through the vertex. And you can see kind of if you were to fold or maybe flip across this line, it would look like the parabola didn't change at all. So that's what it means it's symmetric about here. This is reflection symmetry in this case. And then the last thing I want to tell you is that a parabola opens upward if a is greater than 0. Remember, a cannot be equal to 0. And it opens downward if a is less than 0. So those are the two options. A is greater than 0, opens upward. And a is less than 0, opens downward. And actually I have a Desmos thing here for us. So why don't we go ahead and take a look at that. Here it is, our function ax squared plus bx plus c. And we want to see kind of what do each one of these values change. So first of all, the c value right here, this plus c, the claim is this is going to change just the y-intercept. So this is going to move it up and down. There we go. So the a value, like I said, if a is positive, it opens upward. So you can see it's opening upward right now. If a is negative, it opens downward. So you can see there, and I can raise up the c value if I'd like. And a in general has something to do with like the steepness here, right? So the rate at which it opens. Remember we said that a should not be equal to 0. What happens if a is equal to 0, right? I can go ahead and just type in here a equals 0. And it turns out, right, nothing really blows up or anything like that. It's just, it's not a quadratic, right? This is a straight line. So that's the only reason that we don't allow a to be equal to 0 is because, well, we want this to be a true quadratic. If a is equal to 0, its shape's not a parabola. It's not a true quadratic, right? So here we go. That's why we don't like a equals 0. Not because it really, destroys anything. It's just, it's not a quadratic. And then finally, this b value, this is kind of complicated what this thing does. It's very interesting. It doesn't really change the height, right? The c value here. Maybe, in fact, let me go ahead and plot a point here. I'm going to plot 0, c, right? So you can see 0, c. That stays the same, right? That c value, the y-intercept, doesn't really change at all. But yeah, it's interesting, right? This b value is kind of complicated. It's what's happening here. I've also graphed this point x equals negative b over 2a. So, right, this was this vertical line that had to do with symmetry, right? First of all, you see it hits this vertex, the point at which it turns around. And in fact, I could go ahead and plot maybe one more point, right? If I did negative b divided by 2a and f of negative b divided by 2a, you can see that this point, I guess it's in purple right here, this is the vertex. Notice if I change these, yep, the vertex changes along with it. So this vertical line right here, this vertical line, this is something about this axis of symmetry. This is the thing that if you flipped over this vertical line, the graph is symmetric, right? It would look like it never changed. Okay, so that's what our quadratic looks like. These are some properties. Just to remind ourselves, right, quadratic formula, it's good to have this in our notes. Quadratic formula is equal to negative b plus or minus the square root of b squared minus 4ac, all that's under the square root, all divided by 2a, right? And the claim is this gives us the x-intercepts when y is equal to 0. This gives us x-intercepts, ints, right? So in fact, let's go ahead back on Desmos really quick. I'll graph one more point. I'm going to do the point, well, the y value should be 0, and the x value should be, oh, this is going to be a big fraction here. Let's see if I can do this. Negative b, I'll do the plus 1, plus square root of b squared minus 4ac, all divided by 2a. And look, that green point actually is where it crosses. And notice even as this changes and everything, ooh, look, that's interesting. Right here I don't have an x-intercept. I guess we don't always have x-intercepts, only for sometimes. Right, there we go. And again, as our b values change, there it goes. And of course, the other one is given by, right, this is plus or minus. So there's the plus 1. If I do the minus 1, this gives us the other one over here. So the one that's to the left. So, yep, there it goes. Yep, kind of for any of these values, you can see, oh, sometimes it doesn't exist, but when it does, there it is. Okay. So that gives us the x-intercepts when y equals 0. So that's why our y value here, right, the other coordinate was 0. Y had to be 0, and it crossed at this point here. Okay, so let's go ahead and move on. Let's practice really quick, and then we'll do a model. So find the x-intercepts of the vertex. F of x equals 2x squared plus 3x plus 4, and I forgot, and vertex, right? So the x-intercepts. So usually what happens here is that I sit and I think about this. I try to stare at this and I think, can I factor it? This one's hard. I don't think I can. So I'm going to go ahead and, right, whenever you can't factor, right, because of course up here, and you've probably come across this before, right, sometimes you can factor. It's not all the times. Not everyone can be factored. So, okay, let's go ahead and use the quadratic formula then. So the quadratic formula says that this should be x is equal to negative b. So here's my b value, right? It's the thing that's next to the x. Remember, we're using this ax squared. So a is the thing next to the x squared, bx, so b is the thing next to the x, and c is the thing that's all by itself, right? That's what we need in order to use the quadratic formula. So my a value is 2, my b value is 3, and my c value is 4. Yeah, that's funny. So, okay, let me move this down a little bit then. So we have x is equal to negative b plus or minus the square root of b squared, right, 3 squared is 9, minus 4ac, all divided by 2a. So let's go ahead and simplify this down. Negative 3 plus or minus, this is going to be root 9 minus, let's see, 4 times 2 times 4, that's going to be 8 times 4, that's going to be 32, all divided by 4. Negative 3 plus or minus the square root. Okay, this should be what? Negative 23 divided by 4. So this is where my x-intercepts would be, right? But I don't like this fact that I have a negative under the square root. Right? We do not like negative under the square root. Oops, I erased too much. So this means that my answers are not real. And in fact, if I was to go back here really quick, and if I was to plug in my a value is 2, my b value is 3, and my c value is 4, notice that they don't cross. It doesn't cross the x-axis. It doesn't have x-intercepts. It never intersects the x-axis. Okay, so this means that there are no x-intercepts. None. There are no real ones, right? Imaginary. So there are no real ones, no real places where this crosses. Thank goodness we're only dealing with real numbers, right? Complex numbers. Ooh, would not like to do complex calculus. Okay, the last thing is vertex. There should be a vertex, right? So let's go ahead. The vertex is given by, well, the x-coordinate is given by negative b over 2a. So this is going to be negative 3 divided by 2a. So this is going to be negative 3/4. But the vertex is a point, right? It has an x-coordinate and a y-coordinate. So in order to get the y-coordinate, I'm going to go ahead and plug this in. Right? Remember, back up here. Here's the x-coordinate, and the y-coordinate we get by just plugging in that number into the function. So let's go ahead and see what that gives us. So when I plug in negative 3/4, that's going to be 2 negative 3/4 squared plus 3 negative 3/4 plus 4. Alright, so this isn't going to be super fun, but we can do it. So let's see, 2 and 9/16. Alright, that's when I square negative 3/4. And then I get, let's see, 9/4, right? 3 times, negative 3. So let's go ahead and change that plus right there to a minus. And then plus 4. So let's see, this is going to cancel a little bit, and I'm going to get 9/8. Let's go ahead and make this negative 18/8, right? Because 9/4, so let's double both of those. And then let's multiply this by 8, so this is going to be 32/8 is the same thing as 4. So let's see, 9 minus 18, that would be negative 9, and then plus 32. So negative 9 plus 32. So that's going to be 23/8. So there we are. Let's go ahead and check, right? We can graph this thing. Or in fact, I already have a graph of it right here. So first of all, right, we're very interested in this vertex point. Let me go ahead and try to zoom in here. So this vertex point here is happening, yes, oops, I was hoping that negative let's see, 7.5, so 0.75, that's going to be negative 3/4. And then 2.875, let's see what that, right, our answer that we got was 23/8. So let's go ahead and plug that in really quick. 23/8, 2.875. Very nice. So this is the vertex, right? And so, oops, there we are. So remember, the vertex always has an x-coordinate and a y-coordinate. So we're going to do the vertex is a point, oops, R in there. Vertex is the point negative 3/4, comma, 23/8. There we go. So that's our final answer. And remember, there are no x-intercepts. No x-intercepts. Okay. So that's a little bit of a warm-up here. Let's go ahead and get into an application, right? So an application that we're going to be doing has to do with money, right? So this is the economics version. So revenue. Revenue is the resulting from one or more business transaction. Right. Okay. Recall that the revenue resulting from one or more business transactions is the total payment received. There we go. Thus, if Q units of some item are sold at, oh, this is a typo here. Q units are sold at P dollars per unit. The revenue from the sale, right? So Q units, P dollars, right? This is going to be revenue. Usually we denote this with an R, is equal to P, the price per unit, times the number of units. So, right, if I sell socks and I sell 10 socks at $2 each, I would get $20, right? You multiply these things together. So let's try it out. I paid a marketing company, probably way too much, to find out what the demand is, right? How many units would I sell for my new video game, Ryan's Great Calculus Adventure. And the claim is the marketing company came back to me and said, well, you're going to sell about this much right here, depending on what the price is, right? So, for instance, if you gave them away for free, right? So if the price was 0, and this went away completely, the claim is 10 people would want them, right? There we go. So apparently there's not a lot of demand for Ryan's Great Calculus Adventure. So, okay. Q is the quantity of games that I would sell, and of course you can imagine the more that you charge, the higher the cost, probably fewer people are going to buy them. So that's why this is nice linear, but it's going down, unfortunately. Right? The higher the price, the fewer people will buy them. So what price should I sell them for in order to maximize my revenue? Right? I'm interested in maximizing the amount of money I get. Right? And then how much money would I then make? So my revenue, right, the thing that I want to maximize is going to be, well, P times Q. So P times, and in fact Q is given by this thing right here, negative 0.4 P. And so you can see that if I was to expand this a little bit, right, negative 0.4 P squared plus 10P, right, so this is me distributing P to each one of these things. Rearranging a little bit. If I was to distribute, this looks awfully quadratic, right? Maybe if I put a plus 0 here, now this really looks quadratic. So this is the thing that I want to maximize. Well, actually, let's go ahead and plot this really quick in my graph. So I'm going to go ahead, maybe destroy a lot of these things. Gone, 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 gone. Okay. So my revenue that depends on P is equal to negative 0.4 P squared plus 10P. And if you like, plus 0, right? So hopefully I zoom out of this thing and, oh, there you can see it's a nice quadratic. Right? So this thing is quadratic. And this is the thing that I want to maximize. And so if I'm interested in maximizing a quadratic that opens down, right? Notice that it opens down because my A value here, my A value is negative 0.4. There's my B value, there's my C value. So my A value is negative, so we knew that it was going to be opening down. If I'm interested in maximizing a quadratic that's opening down, then I'm very interested in where does it turn around, right? I'm very interested in this vertex, right? And so the claim is there's the vertex. So I could solve this using my calculator. And in fact, our TI-83s and TI-84s can do this for us as well. There under the calculate, there's a max value, so it could tell us exactly what that is. But let's imagine that we didn't have our calculators, or at least, we want to do a little bit of algebra to show our work here. So let's go ahead back here. And I want to know then, where is the vertex? So all of this setup right here is asking us, essentially, where is the vertex? Because that's going to maximize the amount of money that I'm making. So I can get the vertex, right? The vertex is given to me by negative b over 2a. So I guess in this case, my independent variable is not x, it's actually p. So right, p should be negative b divided by 2a. So that's going to be negative 10 divided by 2a. So if I plot this in my calculator, let's go ahead and bring out my actual calculator here. So let's see, negative 10 divided by, and I'm going to divide all of it, so I'm going to use parentheses here, 2 times negative 0.4, and hopefully if I do things right, well, we already know the answer, right? It's supposed to be like 12.5. It is. Great. So my answer here is 12.5. So this is the amount of money. This is my p-value, my price, right? How much should I sell this game for? P dollars, $12.5. And if I sell it for $12.5, the question is, how much money should I make? How much would I project? So this 12.5, this is what I'm going to plug in to my revenue function, right? There it is. So my revenue function is going to be 12.5, oops, brought the point in a little bit too early, 12.5 times 10 minus 0.4 times 12.5. Okay, let's go ahead and bring out my calculator again. So I have 12.5 times, and in parentheses, I'm going to have 10 minus 0.4, parentheses, 12.5, close parentheses, enter. Oops. You know what? It doesn't like, here I need to specify that I'm multiplying. So I'm going to insert in a multiplication sign. Okay, now enter. Oh no. I have no idea then. Oh, you know what? I see it. There we go. That minus sign right there, right? This is the negative sign. I want the actual minus sign. How silly. There we go. 62.5. 62.5, and this is my revenue. This is how much money I would stand to make. And of course, when I go back here, this is exactly the output here, 62.5. That is the height of my vertex. That is how much money I'd be making. So I guess I'll hold off on making Ryan's Great Calculus Adventure. I can, it's probably a lot of work for $62, right? All right, so there we are. That is how we can use quadratics to actually model real-world situations. That is the end of 2.1. I'll see you guys next time here in 2.2. We're going to move on to exponential functions. I know you've been waiting for them. All right, see you then.